So let's just see that. You can see my screen. Okay, the first thing someone asked me, I think one person asked me was that in the week 9 notes, I had given the exercises, try to see what's going on here. Why is this true, or why are these things true? And how do you find the least square estimate or something like this is what someone asked me last time. Let me just go through a calculation that sort of tells you how to do that. So let's take this linear model that I have here. Now let's go to the. Let me make it white. Okay, so I think right. So this was let's say this is the model we had. So and then okay. the the question was that how do I go about estimating any of these things? Um, so like we discussed long time back, maybe way back in the beginning of the class, that you cannot estimate all the time. So there are identifiable or estimable issues for example. So why is that? Let me just quickly recall that. So in this particular model, we would assume that these epsilon, the errors are distributed like, let's say, as normal with mean zero and some fixed variance, sigma squared, and they're IID, so they're independent. So every data point is independent, that's something. So I can't estimate all the parameters, and so let's look at my eyes. Let's say my eyes were take this again. Let's copy this down. So my eyes were in this range, let's say 1 to k, and then j is from 1 to ni. So the reason for that was that I could always make a new model in which I will just not a new model. I'll take a parameter space in which mu tilde was the same mu as the old mu, and mu I tilde I just moved it around. So I took mu plus, and then mu I. So I added let's say I added a plus c to the mu or the overall mean, and I subtracted it from the individual means. If I did this, uh, and I could go and write down my yij tilde as uh, as mu tilde plus mu I tilde plus the same epsilon ij that I had before. So this model is star, let's say, or plus, and this model is star. See, the issue is that uh, if you just think a little bit, um, yij has the same distribution as yij tilde because the models are the same. Even though I've written it in a different manner, mu plus mu I tilde is same as mu plus mu I. So thus, in this particular thing, you cannot estimate every parameter unless you have some conditions in some sense. So that's why in this exercise, I had given things that I could estimate from this model, the identifiable parameters. So let's look at one simple, let's say if you want to estimate, so you cannot estimate all parameters. So you cannot estimate all parameters. But you can sort of, we'll try to see, you can estimate mu plus mu I. That's okay. You can't identify mu n for each I. This is okay to do. So I'll just tell you this is okay. So let's see how to do this. Let's say this is okay. So let's try and justify how to do this in a second. So the the trick here is the following. So now, given that if I want to estimate only mu plus mu I, this identifiable issue will not come into place because mu tilde plus mu tilde I is the same as mu plus mu I. So no matter how I perturb the coordinates in my own field. So let's try and do this. So let's try and do a simple thing like this. So now uh, I'll just do a a simple notational change. I will set beta I to be equal to mu plus mu I, right? Then I go here and I go here and I rewrite this model as copy, and I want to estimate. So here I just change this to beta I. Beta. So now this is a very simple model now. This we know how to estimate the beta hat, and it's not hard to do at all. So let's just do that. Since somebody asked me last time, I'll just do that. Let's even a simple calculation: 1 plus I less than equal to k, and 1 less than equal to j less than equal to ni. So then what you do, you would have to write down y as x beta uh, plus epsilon. That's the linear model that you have in mind. Then you know that if you want to set this for all I. So, right? And then you want to estimate for each I. So now we know that beta taken, let's take an I, and then you know that beta I is just going to be equal to P transpose beta, and P depends on I in fact. But what is P? P is going to be uh, 0 everywhere, and then 1 in the ith position, and again 0 everywhere else. That's what P is going to be. This is the ith position. So you want to estimate P transpose beta. This is what beta I is going to be. And this you already know that the least square estimate for P transpose beta was the same as P transpose beta hat, where beta hat solved the normal equation. It was X transpose X beta is equal to X transpose Y. Right? That's what we thought we'd get this, right? So that's how you get the answer that. Now, what's our X here? X is just very simple, right? X is just 1. So how's your X here? Here, our X is what now? Your X. So we need Y equal to X beta plus epsilon. And so X should, and then so X should be, if you just think a little bit, X should be what now? Let's see. So now here I have, let me get this down here. And then let's see if you agree with me in this. So I have Y equal to X beta. So beta is beta 1 to beta k. And so the first k guys will have beta 1s. After they're all zeros, right? So essentially I'll have X is just 1, 1, 1, 1 up to the first k things in, sorry, beta 1 in the first n1 guys here. So 1, 1, 1, 1 up to n1. That'll be the thing. And everywhere else is 0 here. It's all zeros here because I don't want to capture anybody in the y1s. Right? And then the next n2 rows, I will just put, let me just do it like this. And then I'll put 0 all the way here. Right? And then the next n2 rows, I'll put 1, 1, 1, 1, 1. The second column, so that'll be the next n2 rows. Second population, and I have zeros again everywhere else. That's how this thing look like, and it will proceed so on and so forth. Finally, at the last guy, I'll get at the nth kth rows of the last guy, I'll get 1, 1, 1, 1 here, and then 0 everywhere else here. That's how the matrix would look like finally. X would look like. Right? And then if you look at X transpose X, so simple. So X transpose X would just be simply, if you just think a little bit, X transpose would be just one in the first, it'd be rows would be 1, then X transpose. So I just get n1 in the first row, first entry, and then 0 everywhere else, and similar 0 everywhere else here. And then it will be n2 in the second one, and else, and so on and so forth, nk in this entry. And that's what X transpose. And then X transpose Y, if you look at X transpose Y, so X transpose Y, X transpose is one of the first thing, right? So the first guy would give you, the first entry would give you the first n1 sums of Y. So ij equal to 1 to n1. N1 of Y1J, right? That's Y1J, so not one of Yij. So X transpose Y will look like. And then the last guy would look like the sum from J equal to 1 to N1 Nk of Ykj. Right? That's how it looks like. And then you want to solve for X transpose X. Beta is equal to X transpose Y. And that's fairly trivial, right? Because there's a diagonal matrix that would just immediately imply that beta hat I would just be the sum from J equal to 1 to Ni of a Yij. And that's exactly what I wanted anyway. So it's not really, so I could do this. So let me just go back and see if you, let me make a double window of this and see if you guys got it. Let me see if I can recall a little bit. So is this calculation clear? That so something you just do it, right? You just have to identify the P here. The P was just trivial. So you do yeah. That's how you do everything. Just look at the estimate with the same thing and standard the same way. So of course now the trick is to the key coveted part of this whole thing is that suppose they tell you go estimate something and it's not estimable, then you're in trouble. So then you're just I did it in this case it was trivial that I wrote the model a little differently and I got the answer immediately. But in general, the identifiable issues again that I've defined before, right? I've said P transpose beta is estimable if P is in the column space of X transpose X, and then and so on so on. You work with that. That means you find the L for which X transpose L is equal to Y and so on. So on. Okay, very cool. Okay, so somebody, the next question was asked in the last live session was the following, that let me just break this across now. Maybe it's very good. Was the following question. They felt that they felt that they didn't understand what a two-way classification was doing. Uh, uh, what two-way classification was doing in that sense, like not this table, this one. Like what was it exactly doing? Why? So because I just done it like a sort of a I said, I have treatments, I have blocks, and this is what I'm doing. So the way I motivated last time was that I said, okay, fine. Hey, I have some number of treatments. I think of each block as some agricultural land, and I put the treatment in each block, and I just check if if all these blocks behave the same way, all these blocks behave the same way in terms of some land quality, and I put these treatments across these guys, and I see if there's any difference in the things. That's why I'm motivated as. But let me try to do today a little bit different way of motivating this two-way classification, and then I'll come back and we'll try and do a code for the one-way classification, and you can try the code for the two-way. So if there are no further questions, I'll carry on this way, but otherwise, I'll stop for a second or so and let me know.
Sure, this is Patrick. So just a quick on the this continuation of this, if you could just go back to the notes of week 11 that you've had on the screen, the one which had the dark screen in it.
Yeah, so
Where you had the
you're breaking
new
up.
one.
You're breaking a little bit, but I think you want me to go back here. I've gone here. Yes, go ahead. No?
Yeah, if you can go back to the where there is mu1 minus mu2, the one-way classification itself,
Okay.
where we are estimating parameters, right? So
Right. Yeah.
just go right up to the.
Yeah.
Yeah, so there is a vector. So here you're doing mu1 minus mu2. You start off with mu plus sum of mu I,
Right. Yeah.
which is the overall mean effect, and then you have mu1 minus mu2 minus mu3, and so
Yeah.
on.
Right. Yeah. Right. Yeah.
How does that come about? Or
How do I estimate this? You mean?
I mean, why this specific construct, or is just an example, is it,
These are just
or
examples of mine. Why? Suppose I give you a model like this. This will tell you if the how different are the two means, two group means, the mu2 and the mu1s. That's all.
Oh, okay.
That's all. Just an object of interest would be these guys. For example, like this is a set of estimates this is a set of objects I can estimate from the model. That's for example, I gave you an estimable class
Right,
of
this is just an example.
as an example. I mean, it's not the only one. Of course, you know, I have done this before, right? I've said that you can go and do P transpose beta estimable if this P is in the column space, right? So
Correct. Yeah.
so mathematically, that's how you do it. But interestingly, these are things that you're interested in some sense.
Right. Okay.
But you know now how to do this, right? Because even mu1 minus mu2 is the same as my beta1 minus beta2, right? That's all it is, right? So if I take beta1 minus beta2, I get mu1 minus mu2, right? Because mu cancels off.
Right. Right. So this
The
is how to
moment I do
define
this,
beta
the
one.
moment I do this, I'm done. I do a different P and I get the answer. Right?
Okay. Yeah. Thank you.
Is this clear to everybody else in the room? Okay, good. So maybe I'll proceed with this idea of why. I'll try to give a different motivation for this particular model, this two-way classification, and rather than the way I did last time in all the videos. So you have a somewhat different motivation. So let's say we are doing the following experiment. Let's say I want to understand some parameter in my body. Let's say uh, sugar value or some cholesterol value, depending on how much fruit I eat and how much exercise I do. Suppose that was the and so let's say I'm just giving a completely artificial example, but this is sort of relevant. The numbers will be odd, but so let's say um, so cholesterol values. I know cholesterol spelling. I'm not too sure. Let's see if I can Google and find out spelling cholesterol. Let me something else. Let me do, let's say, a blood pressure. Let's say blood pressure values and versus let's say I do one thing I monitor is that how much fruit a person takes every day or what let's say one fruit. Let's say apple. Say effect of eating apple. Uh, Eating one apple, consuming one apple, and the other one is uh, so let's say this is blood pressure monitoring, and I have two quantities. Let's say one quantity is my treatment, which I think of it as eating one apple a day, and let's say the other some exercise. Let's say I do walking, say walking, and then in both these guys, I do a little Zolomon monitor. But how am I going to identify different ways people consume apple is that I'm going to say, okay, fine. Some people will consume it daily, okay, and some people will consume it weekly. Okay, so let's say three of us consume it weekly and three of us consume it daily. That's what we do. Okay, that's the frequency of consumption of apple. And let's just do one apple. And walk, let's classify it a little differently. Let's say we don't walk at all, so no walking. Let's say some people walk a little less, let's say maybe 20 minutes walks. Some people walk every day 30 minutes, and some people walk, let's say, is medium, let's say high, let's say low, medium, high, let's say 1 hour, 60 minutes. Maybe lowest 10, let's put 10 minutes, 30 minutes. So this is the amount people walk, and we are groups people. What I will do is I will go and split my population. I'll make them the same group population. I will, let's say I take 40 people. So let's say I take 40 people. We take 40 people. And then what I'll do is we split them into groups. There are four groups in walking, right? So we'll split them into four groups first. So split them into four groups. So 10 groups each. So four groups, four walking groups. Let's call it four walking groups. Uh, Four walking groups of 10 each. 10 each. And then what I'll do is within each walking group, I'll split them again into let's say each group, I split them into 5 people each. 5 consume daily apple, one apple, 5 consume. So within each of the walking groups, so each walking group, I'll split them into 5 who consume one apple daily and 5 who consume one apple weekly. Okay. Okay. So now the black is the response variable. I'm going to check this is the response variable, right? So let me call this the response variable. So the response variable is black. That's my Y's. So for everybody, I'm going to go monitor the blood pressure. That's my Y. And then you think of the apples and the walk are factors. These are factors, right? Let's call this factor one is apple, and factor two is walking. Okay? So and then what do you want to understand? Let's say this is the overall experiment you're trying to this is the overall sort of experiment that we're doing, or we're trying to understand. Now, what are the questions you want to understand? Let's say, for example, you may want to understand the following question. Let's say you want questions to understand. You may want to understand as a practitioner, does walking affect blood pressure? That's a simple thing. Does walking affect blood pressure? That's a very simple thing you'd like to understand. Right? The other thing you understand is that does consumption does so now here I'm giving everybody one apple either daily or weekly, right? So you can just say does consuming frequency of apple. So let me make a screen. Let's see if it changes the screen a little bit. I don't think it does that. My my handwriting is a little better if the iPad is this way. Consuming frequency of apple affect blood pressure. Right? This is one thing one could sort of think about. Right? The then of course the crucial thing you understand is that um, are they connected? So suppose I'm is uh, consuming frequency of apple related to or dependent on or is there a dependency or is a connection or is dependent on, let's say, let me call it dependent, or or does it interact with walking habits? Okay, so with walking habits. So these are natural questions anybody will ask. Like if they're in the real world, if they want to do this is there interaction between two effects? So does walking have an effect on on somebody, and is it dependent also? If you walk so much and eat one apple a day, that means your blood pressure is so much. If there's an and effect rather than independent effect of it. This is something that these are questions that people like to understand. So this is why it's a two-way ANOVA. So one is independently you can observe each effect, that is each quality of walking and consuming apple. The other one is there an interaction? So this is the interaction effect. So that's why it's called a two-way ANOVA. This is the interaction. So this is the interaction. This is the interaction. And this is the individual ones. Right? This is the one. Very cool. So this is the broad this is what one would consider as a two-way ANOVA. And this is one typical situation where you use two-way ANOVA. So you have two factors and you have one response variable, and you don't want to know what each one would do. You want to know what would they do together. That's the idea. Okay. So when you organize the table, I'll organize it the way I organize the table here, exactly this way, but I'll do a little bit simpler one. So let me just copy this table and I'll take it that side, and I will just do the same thing. Maybe I'll do a new table. How's that? Okay, this table looks kind of cute and neat. Let me do a new table. So what I would do is I would do the same thing. I would just have on one side I would put my five daily people of Apple, right? So people who eat apple daily. So I'll put daily. One guy right here comes here. The first group, the second group comes here, right? Third group comes here. The fourth group comes here, and the fifth group comes here. That's the first five groups of people who eat apple. Then I would sorry, just copy this picture down. I'll do the whole thing. I'll put it again here. Do a second group of people, and let's say these will do. So these are all daily people, right? So let me do all daily people, and this is all weekly people, right? So that's how I would put my people down. So weekly, sorry. Okay, so let me just put daily. I put the daily guys. These are all daily people, and these are all the weekly people. Okay. Then on the other side, what I would do is I would go classify the walk guys. So I'll put each person in this block. So first guy is walking, doesn't walk at all. This is no walk. Right. The second group of people go and do this. They walk 10 minutes, and the third group of people go and walk 30 minutes, and the fourth group of people walk 60 minutes, right? And then this is the thing. And then in each of these things, I would just go and put my yij, right? That's my response variable, yij. So if I put a yij here, this person walked 10 minutes every day and eats apple once weekly. That's what this yij represents. And this is the data set I will use now in my analysis, right? And again, I have this model in which I say that let's go back here. So I go back to the model. I have the same model right here. So I'll think of it as y is equal to this plus beta j. This is the model I'll assume. Color black so you can see it. So this is the overall mean is the mu, right? Alpha I is the mean of either the daily guy or the thing. So my I is just 1 and 2, right? So I is just 1 and comma 2. So I is just daily and weekly. I'll call it D and W. And J is just one of four characters, right? No 10 minutes, 30 minutes, and 60 minutes. Right? That's my J. Right down below. So I is just 1. It's just daily or weekly. And J is just none, 10, 30, and 60. And all my epsilon ij's are just always normal with mean 0 and sigma squared and I. So is this clear? The person who asked me how this I'll make it double so you can all check the whole thing together. So let's see, let me go back here. There's live session right here. But again, just have to go horizontal now. Just horizontal. Oops, sorry. Oh, sorry, my iPad went fat. Give me a second, I'll start share again. Sorry about it. So let's see, this is this one, and this. So now is it clear how the model is set up? Someone asked me last time they were kind of lost at what the model was doing. Yeah, you can just mention on chat if at least the model setup is clear for everybody. Even if you didn't ask the question, is the model setup clear? Then you go and do the analysis like we did before, right? We just go and look at, like we did the last time. We have the N is total number of people in the population. M is the number of factors you have. R is the degree of freedom that you get. And then you have to verify that these are the estimable parameters. This I didn't verify, but this you can verify the estimable parameters. And then you try to find the appropriate least squares. And then do the whole thing. And then the testing parameters set up. Thanks. So now so maybe on my notes, I don't know why they have this crap at the bottom. I do not know why. Maybe somebody asked a question last time in R and I put it right there. So maybe does anybody have any questions right now? I can tell you what I want to do today. And then, okay. Quite cool. Okay. So I think two new people, Mohit and Anushka, is it clear to you guys? You can mention on chat if it's clear or not clear. Right.
It's clear, sir.
Okay.
So I have one like separate question.
Oh, which one?
Sir, like for the different hypothesis testing, like we have multiple hypotheses, right? For one in which we check if the variance between groups is zero or not, and another one in which we check if the grand mean is zero or not. So like how do we go about testing for the different hypotheses?
So you have to testing comes from the fact that you have to develop a statistic that estimates the parameters, and you have to find a statistic that assesses the deviation from the parameters that you want to test on, hypothesis you want to test on. So this is something that's you go back to your basics that I did a couple of weeks back or 3 weeks back, I'm not sure, when I said that if you just have y equal to beta x plus c in one variable, and you want to test if beta is positive or not, beta zero or not. So then you have to develop a statistic under which you know the distribution of the statistic when beta is zero. So then assuming that distribution and you compute the statistic values from the data set, you check if that is in consonant with the behavior of the distribution when beta is equal to 0. So I don't know if that, maybe I said too many things in abstract to answer your question, but maybe let's do the following. Maybe I'll do the one-way ANOVA by hand. That way, this one-way classification by hand. And once we do it by hand, we can just go and check why that whole thing. We'll just do this test by hand and see why that's true. Would that be
Yes, sir, that would work.
let's try that. Let's try that. Don't call me sir, call me Siva. Sir, I'll call all of you aunties now. Anushka, you had a question, or can I go on? Okay. So I guess let's do a simple one-way ANOVA, and then we'll come back to this in a second. We'll come back to this. The same thing I think once you get the handle of how to do one-way ANOVA itself, everything else is automatic. After that, it's not really. So let's do a one-way ANOVA example. Right. So again, sorry, I don't know why I killed this. Okay, it's good. Let's go here. So the one-way ANOVA example is the following. When I did this, let's do a simple one. Let's say let's, instead of making this very complicated with ni's and k's and stuff like that, let's just do a simple one. Let's say we have three graders. Let's say three graders. So let's say three graders. And I want to check if they're all let's say quote unquote maybe similar. That is similar. So what I would do, I would divide up my class into what I think are similar people of 10 sets each. Let's say I give 10 sets of students to each grader, 10 exams, 10 exams, exam scripts. Okay, so these exam scripts are all similar in some sense. Like they have similar distribution. So similar distribution. That is, if the graders are the same, they would give the same scores to everybody. And I would give 3 sets. 3 sets I would take out of 3 sets. Then I would go and I'll give 1 set to each grader. So grader 1, grader 2, and grader 3 would get 1 set each. And each one would record their scores. Let's say Y11 is the record score of the grader in. So here, since I'm putting Yij's, I'll keep this as Y12. This is let's say Y110 is this guy. And this person would give the scores as Y21 all the way to Y210. And this person is Y31 all the way to Y310. Right. So I have 10 scores each from each grader. So I have 10 scores each. So I ask each grader to grade it out of 100. Each grader gives a score out of 100. For 10 answer scripts. And then instead of writing it like this, so I have a Yij for everybody. So then I have to assume now from this Yij, can I tell if so one simple assessment is that how do you assess the grades are different is that you just see if the mean score given by the graders are truly different. So of course you can calculate the mean and see if they are the same, but you can check if under assumption of normality, if the mean score of each grader of mean score of each grader is statistically significant, statistically different, is different, is truly different. It is and can you say is different with some statistical significance? Is what I want to do. So that means the same way like before, I have a mean mu1 here from this guy. I have a mean mu2 here from this guy. I have a mean mu3 here from this guy. And I want to test is my null hypothesis is that they're all the same. That is mu1 is equal to mu2 is equal to mu3. That's my null hypothesis. So I want to test this hypothesis. Very cool. So how do I go about doing this, right? So that's what I would do. So now let me just send you an R code, so and then a data set as well, and then let's try and play with it a little bit. Let's see, send it on chat. Let's see how to send on chat now. I have to go here, file, document. Give me for a second. Let me see if I can find it. Very good. I think it's data1.csv. I think I'll give it to you in a second, and then I'll give this to you. Let's see if this is the one. Yeah, this is the one. This is the one. Let's see. Take this one. Let's see if it's there. Okay, that's the data set. Let me open up my data set. Let's see if that's the correct one. This is what I sent you. That looks correct. I think let's take that. That's very cool. Yeah. So that's the grades that I've given to you. And now let me also give you an R code that let's try and play with. So I'll stop sharing. I'll go back to my R code. Maybe I'll share my screen a little different way. So I wrote down the one-way analysis code by hand. So for these two things. So can you all load up R Studio and put the data file in the appropriate, and we'll play with it in a second. So let me first try to see how to do this. Give me a second. So while I set my things up, can you all just set your end up, load up the thing on RStudio, and put the data file in the correct directory. Let's see if it comes correctly. Some problem with this cable. You give me a second, I'll come. I'll just load up this thing, I'll come in a second. Can you all let me know on chat if you have already loaded up on R and have the CSV file also ready? We can just. I will, okay, good. Very good. So let me share screen. Have others done it? Like Mohit. Okay, guess we'll be left. Prashant has done it. I'm not sure. Okay, let me share my screen and I'll start. I'll start the thing. So I'll share my desktop for a while. Let's see if it works. Okay, can you all see my screen? The R on the left hand side and my iPad right hand side. Yeah, very good. So you can see the screen. Okay, very good. Let's try and play with it a little bit. So now I want to do I have these three scores. So first I did an artificial one. Let's try and come to the second, the artificial one. So here I just said that I generated we'll come back to R data in a second. So this comment 9 should be recent data set again. Okay. Data set again. Let's see, data set. I think data 1 is what I sent everybody. I sent everybody. Let's see if it's okay. Okay, I've sent it again. And I've also I'll send the program also. Very good. Okay, I've sent it again on chat. Okay, so now let me do this is one. This thing should be one because that's a data set one for you guys. Okay, we'll come back to the second. But let's say we generate 3 artificial data sets square. So here what I do is the first one I generate a normal 10 scores with mean 50 and variance 1. Second one is again 10 scores with mean 75 with variance 1, and C3 should be mean 82 with variance 1. So it's clearly the models the scores are different. Each grader is giving one guy has mean 50, one guy 75, and 82. You think it's different, right? So let's try and see. So what I do is to make this first, I just make it into data frame. I put this into thing and I put DF. So if you let's go look at DF below. DF is just these scores that I have, right? These 10 scores that I have, moves across the side, so it's clear. These 10 scores that I have, and the other various scores. So now I want to do ANOVA on it, right? So let's go back to the ANOVA on the right-hand side of my screen, the iPad screen. Let's go to the notes. So what do I have to do? So I assume the model is this. So let's say the model is this. Let's go back here. Let's say the model is this. So let's say each guy is each yij um, is just give me a second. My pen is not working properly right now. Just need to check. Give me a second. I'll stop sharing. Come back in. Uh, set this pen up. Let's see. Okay, that's not. Let's see if it works now. This here. Where's the our studio gone on the side? Okay, cool. Pen's working again. Go back here. Okay, so the screen again visible now. Let's do it. So now I'm going to use this particular model, y is this, and I want to test. Let's say I assume my mu is 0, and I just want to test if I have yij. So a model I'm going to use for this particular above question is that uh, each of the yij's is going to mu I plus epsilon ij, where epsilon ij is normal. It means 0, and let's say variance 1 for sigma squared. Let's assume variance 1. And then I want to test if mu1 is equal to mu2 is equal to. So my null hypothesis is that they're all the same. That's my null hypothesis. Right? So I want to test. So what do I do first in this exercise? So let's go back. Let's go down here. So I said that I look at the sum of squares total. That comes about as sum of squares within and sum of squares between, right? So let's copy these two things down. So let's copy these two things down. So let's put these things across the other side. Go here, make everybody black so it's clear, everything one line. And in my case, everybody with the same sample. So each group in our case are going to have 10 people each. So I'm not going to give different numbers. So, okay. So N1 is same as N2 is same as N3 is 10. So let me mark that down as 10. This is 10. And in our group, we have 3 groups. So 3 people, 3 graders. So it's 3. Okay. This is what happened, right? So, and then my NIs are all 10. So I just move across and I just put a 10. So maybe I'll just make all these numbers a little bit, in our case, as orange, let's say. So let's make it here. Let's call this as pink. And let's call this guy also as pink. So these are our numbers in this example. That is, we have 10 answer scripts, 3 graders. Right? And Yij here is the score, is a score driven by grader I on answer script J. That's what this is. Right. And this is what I call, this whole thing is what I call as the sum of squares within and sum of squares between. So we mark them as blue and red. So if I mark them as blue, it'll be another disaster. Let's see what happens. Let's see if I can do that cleverly. I can do that very nice. Call it as blue. And so this was this sum of squares within. And this is the between sum of squares. This is between the groups, between the graders. So to calculate these two things. Once I calculate these two things, I showed that here everybody is same, sigma squared is 1. So you know that I know my sum of squares is going to be chi squared each, and the ratio is going to be, so this is something we know. Let's copy this across. This is going to be, so copy this. So something that, this is where what question you asked me, the following, under the null, under H naught, this is where crucial under H naught comes in. Make it black. Let's say I'll make it here. And then let me go back here. Let me go back here, here, here. So let me write this as S is between. So this is under the null. So my K is let me just leave this as K squared this way. Let me write this way. So so the crucial thing is, like, if someone asks me how do I test, is that if H naught is true, this under H naught, the distribution of these two people, this person is chi squared n minus k. N is 30 here, and then this is 30. This is so n is equal to sum of the three groups. That is 10 plus 10 plus 10. That's 30, right? And k is 3. So this is chi squared 27, and this chi squared 2. That's what I got here. That's exactly what I have. Right? And variance is 1, so I'll remove the sigma squared as obviously this sum squared. So this is valid only under H naught. And now I can use this to test. So if my H naught was true, then these two statistics would behave in this fashion. And then I would be able to try and see something about if this hypothesis is true or not. So the way I did it in the thing was, you could do it independently, but if you compare within and between, then this became an F, right? So let's say there's regardless of sigma squared as well, but let's copy this down. Copy it down. Let's go here. So I also know that this guy is an F. Everything's black now. This is an F, right? So the F, and this F is now here is just 2 and 27. So now I can use this. Of course, now in this case, I knew my sigma. Let's say I did not know my sigma squared. I just knew sigma squared was some number here. So sigma squared here, then I would have a sigma squared here and a sigma squared here. But the ratio would be independent of sigma squared, and that's how I get it as F. So now all this is true only under H naught. This is all under H naught. And now I can use the statistic to see if the statistic behave like my F, then I know that my H naught cannot be rejected. If it doesn't behave like my F, then I can reject my F. So what do? I go look at my thing. I go look at the chance that my given statistic. So let me copy this here. So I go and compute the chance that. So let's say instead of writing it like this, let me write it a little differently. So what I will do is, I will rewrite it differently. I'll just go take a Z. So here k minus 1 again is, in my case, k minus 1 is 2, and this is 27. Right? So 27, so let's say 2 here and 27. So what I would do is, I would do the statistic that I have, right? So I have this number I can compute from data set, and then I would try to see, I would take a random variable, let's call it as capital F, that is distributed as the distribution of F with variables 2 and 27, and I would check if the probability of that random variable F is this, what is the chance of this, if how large or how small this probability is. And what I'm going to do is, if this I will go ahead and now fix a confidence level or fix a significance level. I'll fix alpha, a significance level. And once I fix this, so let me call this as my p-value, or I'll just take this, and I won't introduce more jargon. What I'll do is, I will check if this probability, I will check if this particular probability is less than my alpha. Then if this happens, and I know that if that means this chance occurring is very, very small. That means this is very, very small. So it means that if my alpha is so small, then what I'll say is that if this happens with alpha confidence, I'll say that there is evidence that the null hypothesis is not true. There is evidence to reject the null hypothesis. That's what I would do. Okay, that clear? That's the idea. So can you, people on chat, can you let me know if this idea is clear? Like, I don't know how many are left. Okay.
Yeah, Shiva. So this idea is clear.
Yeah.
Just a couple of points. So we have these two ways of checking this significance level, right? So I mean, of course, the proper way is to do this probability, but we also, in some cases, seem to compare the tabulated f value versus the calculated f value,
Yeah, that's right.
and
So
then reject on null
yeah,
hypothesis.
yeah.
So
So
how
I'll
does
take
that work?
the same thing, right? Because just I didn't mean to interrupt you, but let's say I want to check this star, right? Right. So
Right.
what I do is either to a checking star, you can take this thing and then find this thing. Alternatively, what you can do is you can go ahead and calculate the following. You can go and calculate, let's say, let's call this f critical. I call it f sub c. This is what's called the critical value. So this you have it from the f tables. You go and calculate f sub c such that the probability that a random variable f is at least uh, f sub c is going to be equal to alpha. Okay? You calculate that. And then what you do is, if you go and say if this guy is bigger than your f sub c, then you do the same thing. You conclude again. Then you say same thing with alpha confidence. Same thing is it. They are both the same ways of doing this, the same. There's no difference. Does that answer your question somewhat? I'm not sure.
Yes, yes. No, absolutely. So we're basically, instead of yeah, no, I understand. So we're just looking at what is the critical value and then calculating the probability
Yeah,
of
the same thing. I mean, either you go and do this calculation plus once and for all, and then if you have many models, just keep doing this. Just do this check,
Right.
check, or you go and compute this every time. That's the same thing.
Sure. And just one more question. If I were to ask, if my null hypothesis was to, or the test is to check whether the variances differ
Yeah.
between
That's
the
a different
models.
test. That's a different test. You have to work differently. I have not done that till now. You do a different test. I think I may have it in the notes somewhere, but that's a much more complicated test to do.
Or is it because, see, in one of the assignments that we had,
Yeah.
we had to go through exactly the same steps.
Yeah, so there I would assume that the mean is 0, and I would have random effects one, right? That's the one you're talking about. Which one? I'm not sure.
That's correct. Yes.
Yeah, so that's this is similar. See, again, all you have to do is find a statistic that gives you the correct variance, so correct value.
But the statistic still involves the same sum of squares.
That's right. That's right. That's in the random effects model that I've done in the next class. That's right.
Right. Because I think that's where our confusion starts. I mean, at least I think the other person also had the same confusion in a way that there we were doing the exactly same set of steps, but comparing variances.
Correct, because there I assume that all I did was I just moved this is actually random in that case. I just moved the mean out into sigma epsilon ij's, and I just tested for the variance differences.
Right. Okay.
Okay, so let's go with this here. So let's try and do the following. So the first thing I do was I did a fake. Let's go to the left hand side now. I did a fake test. I did a fake data set. So I have 3 things like I did. That's my data frame here before. So now I convert it to my y's that I like. So my y's are like exactly like I have. There's an R, the yij's have to be correct, right? So this is my capital Y. So capital Y like this, the 3 columns of this, no problem, right? So then I look at the capital J and the capital I, and N is I star J. That's what I have here, right? So then that's my total number of people in the sample space. Let's see, N should be 30. Let's go down and check. N is 30, N is 30, and I is 3, and J is 27, right? Very good. There's 10, there's 10. Then I compute the within groups mean first. That's what I have to do on this side. Right? If you look at my guy here, sorry. If you look at the mean, I have to, if I wanted, I had to compute the yi bars and the total means. Right? So that's what I do here on this side, right? I do the first mean on the first group on this side, on the first group on this side. So let me go here. on this side, and the second group, and the third group, and fourth group. So let's do this. So like I did before, let's do bar y1, that's 50, and bar y2 is 74, and then bar y3 is 82. That's what I think. Right? And then bar y, the overall mean, is some number right here. So now clearly this test should give you. So let's say sum of squares between I do, that's exactly what I have. J is the same everywhere, so nothing to be done. Do that, I get this, right? So I have no different. I wrote about Ji typically, but now I have only one J. That's easy to do. Then I do a sum of squares within 1, 2, and 3. I get this. So let's do SSW and SSB. W is this, SSB is this. Oh, sorry. B is this, I get this, very good. So then I go and do the total sum of squares, that is this. Then I compute the mean sum of squares, mean square within, mean square between, mean square total, like I have. And my F statistic is exactly what I have here, right? On this side. This is exactly what I have here, right? Exactly. This is what my F statistic is, right? There. Right? Because N minus I is just 27, and then so I do this, I do my F. So what's my F statistic here? So do you all get this? 3180, what are you getting? I'm not sure. You just confirm on chat, this is what you got. Or you might get something else because you're doing your own data set, right? So okay. Then if I do this, I do I minus 1, I find the F critical. F critical should be the same for both of us. So F critical should be the same. Should be very something like FC should be 3.35. So clearly now my F is huge, right? So it's much bigger. So definitely I did not have. Very good. So now let's go back up and let's load the data set. Let's just start this again. Let's do this. Let's uncomment this. So let's load my data set V and Y. So I have some errors, but let's just ignore that for the time being. So my Y is just the scores that I have. Right? This is correct or no? I'm not sure. DF not be this time. DF is no, my DF is not, oh, I have to set the working directory. I'm sorry. Session set working directory by location. Very good. So let me go here. Very good. Now let me do my DF. No, somehow my data is different, is it? Why is it different? Right. Okay, did I make a mistake here? What is it? Oh, interesting. Let me try it. Why is my mind? The old ones still coming. I'm not sure why. Okay, very good. Now let's see DF. Yeah, now my DF is correct. This is the DF that I have. You should all have the same thing, right? I've called it C1, C2, C3. And so G1, G3. Then I do the Y, I transpose it from again. J is this, I is this, N is this. Let's go look at I. The number of gates is 3. Answer scripts is 20. Answer script is, why is it 27? I only have 9 scripts, is it by mistake? No. Why is it not? Y is this? J is this. Let's go J. What could J? Here, in this case, what have I done for J? So 27 people in each group. Okay. So I've got 27 answer script instead of 10, like I've done here. So, and it's this, that each person is given 27 answer scripts in my thing. N is I star J. Then I have to do the first mean, second mean, bar, and so forth. So let's look at the means. Let's see, bar Y1 is this, bar Y2 is, Y3 is this, bar Y2 is this. So kind of close by. They're not very, very far. They're kind of close by, right? Sorry, what happened to this? So I come here, then I finish this, then I do sum of squares, between, within, this way, and total, this one, I do F. What's my F now? F is quite small. So that means that I don't have enough evidence to reject the hypothesis that they're different because my F critical is the same, right? Let's see what F critical is. F critical is not the same, but it's a little different. So it's like, so FC is 3.1, so it's like almost the same. It's false. That means I don't have evidence with now. Very cool. Can you all let me know in chat if you got similar numbers for at least for the data set that I gave? Yeah, the ANOVA function I have not decided. I have not, that also you can do. I have done it in the recordings, I think. But here I just did it with by hand. So.
Yeah. But just a quick question. When we're calculating that FC critical value,
yeah.
In some places, we're using 0.05 with low tail falls or something like that.
That's right. So I'm just doing the other quantile. That's all. I'm doing 0.95 is the other side. That's all.
So lower tail falls will do the other quantile.
That's right. Listen, this is symmetrical. So this is the probability of the side. That's all. Okay, I'll stop sharing and I'll stop for the day. We've done enough.
Shiva, one last question.
Yeah.
Would it be right to say that the hypothesis being tested depends on the model? So, like a one-way classification model tests if all the means are the same, while a random FX model tests if the variance is zero or not.
Yeah. I think I think it's a little reverse. You have a problem at hand. You have a hypothesis in mind. You set up a model that understands the hypothesis. That's all it is.
Okay. And so for if you wanted to test the hypothesis that the grand mean is zero, then what sort of a model should we use?
You can do the same model. You can just do same model and then just do the sample mean. That's really easy, right? That's just a bunch of normal data, and you want to test for mean. That you can do a normal z-test. You can do, right? There's no problem. You know how to do anything else, right?
Okay.
So here it gets more tricky because you have 2-3 factors and understanding one response variable, right? See,
Okay.
you can go to you do classical hypothesis testing first and then come to these things a little later. So these are much more complicated tests that we're doing right now.
All right.
Okay, so I'll stop for the day if there are no further questions, and we can meet if necessary later on, or on Slack. You can ping me as well.
Thank you so much.
Okay, so I'll close the meeting if there are no further questions, and we can carry on. Yeah. If you guys want one before the final, we can have a review session as well. But let me know on Slack if you want.
Yeah, sure. I mean, one session at least on random effects sometime middle of next week.
Yeah, I don't mind doing that. Just Ishan, can you just coordinate when to do that?
Yeah, sure, Siva. I will do
So
that.
maybe I will also do a code on two-way ANOVA by hand and one random effects by hand. We can do it both by hand and check it. When is the final exam, Ishan?
It's 24th, Siva.
24th, right? So we have next week. Maybe we can meet on the 19th. So that.
Yeah, sure.
Or the weekend, if you want this weekend, we can meet on the 17th evening, if you want, like Sunday evening. But Sunday evening, people don't come. That's why I don't want to do that. Maybe.
I will check the calendar and coordinate with them, and then I will update you.
Yeah. Okay.
Yeah.
I hope it's useful, and thank you. Yeah.
Thank you.
Thank you, Siva.
Okay.